Welcome to the Crunch Review Session Trilogy. Okay, so we're doing tonight, we're doing tomorrow night, and just for variation, we're also doing Thursday night. So the plan is for the tonight and tomorrow to do a complete review of everything you did since the midterm. Okay, as I said in my email, the stuff that we did before the midterm was excellently captured on a video. And I sent the link for that as well. If you did not get it, it's on the Blackboard site, and it was week 6. It's quite a long video. I think it's 3.5 hours or so. But that's everything pre-midterm. I watched portions of it, and it seemed clear enough, or at least as clear as the original was. So I'll let you be the judge of that. So that's the plan. Now, the Thursday session, however, is a Q&A session. So you have to bring questions, and I'll just keep on doing them. And, you know, as long as they're Math 201 questions, I will keep on working on them until we're all exhausted or finished. Okay, there's a chance that I may even have time tomorrow. I'm being a little bit optimistic here because there's quite a lot to cover. But if I finish the review early, then we'll have some time for questions tomorrow. Okay, when I do the Q&A, the questions from the whole course are fair game. I'm not going to restrict that. I'm just not going to do the theory of the pre-midterm stuff. All right. So that's my plan. Now, we are going to take a break since it's 3 hours. We'll take, a 5-10 minute break around the mid-time of the session. Okay, so it turns out in my mind, by the way, there's not that much theory, actually. I mean, there is a lot, but there's more pre-midterm in terms of finicky, different little things. Here, the post-midterm emphasis is on a few large ideas, but the questions, the problems become more involved. So I'll probably be spending more time actually working the examples. But this is the reason I think we may even have a little time for questions tomorrow. So I'll try to maintain a somewhat less frenetic pace than I had to, because we have a little more time. Before I begin with the actual material, I wonder if anyone has any questions, just something on your mind, not a particular math thing, but just about the course. Is there anything? All right. So I thought what I would do is give you a little map. I'm going to start off with a map. And it's a map of all the different integrals. And in fact, it's actually a map of everything, of the entire post-midterm course. So in some sense, almost everything in the course is going to be on these boards over here. All right, by the way, I'm only going to be using the central 4 panels of the boards here, the 2 in the center, because it's sort of dark and people over there can't see, and vice versa for that. Again, this room is the best I could get. It's more space than the fine rooms, and the only problem is it's a little bit dark. So if you have trouble seeing, I do invite you to sort of come up if you need to, if you're at the back or on the sides, and peer at it closely as long as you don't disturb other people. All right, so with those preliminaries in mind, here is my map of all the different types of integrals and the connections between them. And so this, I think, sort of summarizes it. So I'm going to start over here. When you draw this, I sort of put it on a landscape thing. You might want to tip your page, because I'm going to fill up these 4 boards and this little bit of wood here with chalk. Okay, so the first sort of integral, which is not really part of 201, but just an ordinary single integral. So I'm going to give that a little bubble of its own. Okay, well, that's Math 104 stuff, 103. All right. The next sort of integral we looked at was double integrals. And the prototype is f, and I'll just write it as f dA. And R is some region in the plane. Okay, you can come in. Don't mind the video camera. It doesn't bite or anything like that. Just come in, find a seat. All right, so the double integral, that's the prototype. But here are some sort of varieties of double integral that you see. So you'll see f of x dx dy, from some region to some region. When I don't know what it is, I kind of put a little smudge there. Maybe I'll use asterisks there to distinguish from the smudges. This means just something would be filled in there. Or dy dx. You've also got again the smudges. You have f of r theta, r dr d theta, and that's the polar form. And another possibility, or something to be aware of, is that you have the change of variables, otherwise known as substitution or the Jacobian methodology. Okay, so these are three realizations of how to compute these integrals. Now, here are four special types, special cases. So I have curl integrals. Here are two curl integrals. So I'm sort of jumping ahead here. This is, for those of you who just came in, this is a sort of summary of everything I'm going to be talking about. So this is the integral of the curl of a vector field dot k dA. Again, I'm going to be visiting this all in detail. This is the sneak preview, although you know you've already seen the whole course. That's not much of a preview at all. Definitely a review now. Okay, so another way of writing this, let's say, or dn dx minus dm dy dx. So these two here are curl integrals, and they're double integrals. They're just regular old double integrals, but they're of a special function. That's why I'm saying they're special cases. And the importance of them will become clear when I fill in this board and start drawing some arrows. And then the other possibilities go like this. Divergence integrals. I've got two of them as well. So if I take the divergence of a vector field, that's a scalar, so I don't need to dot it with anything. I just take dA, and the other form of that I care about is similar to this, and more specifically the mdx plus dn dy. Oops. dA, actually that one is dx dy, and these are divergence integrals, just in different forms. So that's a sort of potted summary of the different types of double integrals, and I'm going to put that in a little bubble as well. All right, somehow I'm supposed to fit triple integrals down there. So let's try it. It's going to get pretty messy when I draw these arrows. I'll just fit it down here. Triple integral. So the prototype for that is, of course, three integrals over some region, f dv. That's the prototype. The three realizations, I've got to get down on my knees for this. So the integral of f dx dy dz, and of course, now if I roll it, I'm not going to be able to see it. Man, this is a pain. I wish I wrote smaller. How am I going to fit this? You even going to be able to film it? You're going to be able to film it. Well, if you can't see it, just stand up and you'll be able to see it, and then you can write it down. So I've written integral of f dx dy dz or other order. But now I'm going to do a line break and just show the cylindrical, which is a triple integral f, and it's going to look like dz r dr d theta. Or instead, this could be r dr dz d theta. And that's cylindrical. And then finally we have, well, almost finally, we have the spherical version, which is f rho squared sine phi d rho d phi d theta. That's spherical. There's also change of variables. And then really squishing it in here. This is visible on the video? Not quite. Okay, special case. Looks so pretty on the page, but there you go. The special case is just one example where it's the triple integral of, I'll write it in the same notation, the divergence of f dv for some vector field. That's f underline, and that's a divergence integral. And all that are the triple integrals. Okay, so these are, sorry, these are the basic types of integrals, and we're going to be going over them, well, not the single integrals, but we're going to be going over them shortly. Now, there are two other types of integrals that we looked at that reduce to the single integrals. And again, I'll be going over this later tonight, but just, so on this top board, I'll look at line integrals. And the basic prototype is the integral of f ds over some curve C. And just by reminder, ds is, well, I'll write it as r prime of t dt for a parameterization r of t. Again, I'll be going over this later, but just trying to get it down. All right, special cases. Okay, so we have the integral of f dot dr. That's not quite the same thing. Here there's a scalar, little f ds. Here we have a vector f dot dr, and I'm using a capital F with an underline for the vector field. This is sometimes written, and you'll see it occasionally in the past exams, it's sometimes written f dot t ds, where t is the tangent vector field, t ds is the same thing as dr, and I just don't want you to be shocked if you see it. The point is that this is called a work interval. It's a work interval if f is a force field. That's just a physical interpretation that f is a field that shows you what forces objects experience as you put them in there. What's the force pushing them in some direction or other. It could also be called a flow integral if you interpret instead f as a velocity field, like a wind. It tells you how fast fluid is going at a certain point. And it's also called a circulation integral if f is a velocity field and the curve C is a closed loop. You can't really have a circulation around just a little segment. It has to actually be around a closed loop for that to make sense. So that's one type. This reduces to a sort of differential version of it, m dx plus n dy. That's the same thing as a flow. It's a flow integral, work integral, circulation integral, and that's if it so happens that you write f as m comma n and dr is equal to dx dy. And then the other big sort is, instead of doing fdr, this is supposed to be a star here, if you do f dot dn, so this is now a normal to the curve, so this is called a flux integral, and normally that's if C is closed again. To indicate the direction. That's just a convention that reminds you that C is closed. And the way of writing this is that we write this as m dy minus n dx. So that's the differential form version of it. And again, that's if f is mn and dn, the normal, I now think of it as dy comma minus dx. And that corresponds to that. Now, why do I write these things here on the left? So this whole board is in one big bubble. I can't. Yeah. And the point is, any of these line integrals have to reduce in order to compute them, unless you use a special theorem, they need to cross over. This is a guess. Line integral reduce, or line integral reduces to just a regular old single integral. So let's see how well I lined it up. Oh man, that was bad. No, look, I did a good job. Okay. Your arrow is going to have to go all the way across. Now, the reason I mention these special cases is that there's this Green's theorem that allows you to correspond to the special cases down here. So if I really lined it up, I would have lined them up very beautifully. But look, this one here, and your paper will show how that lines up with this. And then this version of it lines up with this. And this version, the flux integral of the normal thing, lines up with this divergence. And this one lines up with this one. So you'll have to work out a good way of doing that. Again, it looks much nicer on my page, but I didn't have to draw across wood on my page.
When you say lines up, what does that mean?
Well, I'm sort of connecting them with some magic line that shows that there's this connection between them. And that connection in all four cases is Green's theorem. So the idea being that they're actually the same thing. So Green's theorem is a sort of glue that allows you to convert one of these line integrals into a double integral, which is a surprise. Okay, so that's the other way of computing them. If you give me a line integral, then either you can convert it, you can reduce it in a one-way operation to a single integral and compute it like that, or if you have one of these special forms, you can change the line integral into a double integral and work it out like that. But this actually goes both ways. If you're going to put arrows on them, then I am going to put double-sided arrows. It's sort of hard to see. So you can actually convert back and forth. Okay, so I'm thinking of these different types of integrals, and this Green's theorem is a glue. It's sort of a link between a line integral, which is really a form of a single integral, and a double integral. But it's a special double integral and a special line integral. Okay? Again, this is just a summary to show you how it all fits together. The last piece in the puzzle is surface integrals. So the surface integral prototype looks like this. It's a double integral over a surface f d sigma. And I'll go over this later, probably tomorrow. But the idea of d sigma, just to remind you for your reference, is that it equals the absolute value of grad g over grad g dot k. As I said, we'll be going over this if the surface is g of x, y, z is a constant. So that's one form of this. And the other possibility is that it's Ru cross product Rv if S is parameterized by R, the vector R of u comma v. So actually, we have two forms for the surface integral. Again, I'm going to go over all of this in detail, but this is the summary. We only had one form of parameterization for the line integral. It's sort of, there's no real nice analog of the first one. I guess you could, but it's sort of, you just don't. So for the surface, there's the two forms of d sigma. Now, again, I have a few special cases, but not many. So the first special case is a flux integral, which is just a special form of the surface integral. And it looks like this. F dot n d sigma. Again, I just want to emphasize that this flux integral is nothing other than a surface integral. It's just the same as this, but F dot n is little f. That's how it reduces. It's the same thing, but it just has a special name. It's called a flux integral. Here, n is the unit normal, and it equals, corresponding to these two cases, in this case, it equals plus or minus grad g over its norm, whereas in the second case, it equals Ru cross Rv over the norm of that, plus or minus. Those are the two forms of the norm. And so that's a flux integral. Now, there's a special case of a flux integral if S is a closed surface. Then the flux integral corresponds with that divergence integral. So you should draw a little line linking those two, and the label on this line is the divergence theorem. So that links a flux integral for a closed surface. I want to say, i.e., no boundary. So again, we have one of our three big theorems linking a surface integral, which is a double integral in spirit, to this. Now, when I said it's a double integral, I guess I need a bubble around here. I've got one more thing to write in the bubble, but it'll fit down there. So the surface integral needs a line going like this. Crossing over here reduces. Somehow on my page I managed to avoid crossing any lines, but I don't know how I did that. Anyway, so the surface integral reduces to double integral. The line integral reduces to single integral when you compute, but then you have these magical links. Green's theorem links again the line integral to double integrals. Here, the divergence theorem links a specific surface integral to a triple integral. And finally, you have one last special case, which is also a flux integral, but it's a flux of curl integral. That's a very technical name for a flux integral of a curl, which looks like this. The curl of f dot n d sigma. Again, that's just a special type of flux integral. But the reason I mention it is now I'm going to try to do some miraculous linkage. How do I fit this damn thing in? This is why it didn't cross. I didn't even sort of put this in. Well, anyway, the thing is, this is supposed to link to the line integral. Oh no, I did link it in. It fits over here. Beautiful. Thank goodness for that. It links over to the circulation integral. So this flux of curl links over to there. And it's a double arrow, and that's Stokes' theorem. Okay, so it's a little bit confusing when you just look at it. Hopefully you understood my explanation and were able to render it. I have a question over here. You are asking me for something that I suspect is physically impossible. No, I cannot move the bottom board up because it doesn't move. No, the lectern is wired in place. You're just going to have to stand up and walk around. I'm so sorry. Yes, I will try to avoid writing in the future on this part of the board, but for this, I could not help it. Question?
So is there just a linkage between the flux and the line integral?
Yes, the Stokes' theorem linkage is a two-way linkage between the flux of curl integral, in fact, and the line integral that is specifically the first two there, especially the first one, the circulation integral. Okay? So you've got three big theorems that link them, and then you've got just the two reductions. So the whole linkage between them can be summarized as follows. Line integrals reduced to single integrals. Surface integrals reduced to double integrals. Triple integrals are just them by themselves. And then the three big theorems have surprising double linkages between certain types of line integrals and double integrals in the case of Green's theorem, flux integrals or surface integrals and triple integrals in the case of Princeton's theorem, and flux of curl integral and circulation integrals in the case of Stokes' theorem. All right, that doesn't tell you what the theorems are, but nevertheless, that's more or less everything in the course there on the two boards, the course post-midterm, or at least a potted summary thereof. The one thing that's really missing is the notion of conservative vector fields, and I guess the other thing that is missing is what it actually means and how to use it. But there it is. If you want to study it, make sure you know everything on there. This is what you need to know. Okay? All right, so we're all done. No, just kidding. Now you have to go into the details. Before I begin with double integrals, just wanted to tell you a few general principles that apply to all of these integrals, all 5 types, but really 4. I'm not counting single integrals anymore because we know them so well. So I'm talking double, triple, line, and surface. Okay, so general integral principles. Okay, I have 3 sort of comments. If the integrand is 1, so if it's one of these integrals of 1 d something, then that is essentially the size. This corresponds to size. So what do I mean by size? Well, it depends if it's double, single. So let me be more elaborative. If it's a double integral, that's the area. If it's a triple integral, so you can have a 1 in there if you like, that's a volume. If, however, it's a line integral, so 1 ds, that's the length of, so I guess area, I'm trying to kind of scrunch this up again. There's a little r underneath there. So it's the area of r. This is the volume of d, since there's a d under there. This is the length of the curve c. And if it's a surface integral, capital S, 1 d sigma, This is the surface area of S. Okay, so in some sense it's just the size of the thing. You're not integrating a complicated function, it's just the function 1. So you just have to interpret that in each case. All right. Comment 2. For any of these integrals, the average value of f over whatever the region is, over the blank, I'll call it a box, is equal to the integral of f d blank over the integral of 1 d blank. Now I'm leaving out the blank, and let's fill the box with cross-hatching to make it clear. Rather than write out 4 separate formulas for each of these 4 types of integral, I thought I would just sort of present a generic version of it. If you have a function defined on a region R, a volume area D, a curve C, or a surface S, and you want to know its average value, you integrate f over whatever that region is with the appropriate integral. So I don't even know how many integrals to write here. Depends what it is. And then you divide by the size of it, which is, in other words, the integral of 1. So you set up the integration, but then you divide by just the same integral with 1. So that's the size from above. Okay, so that's how you find an average of a function. And I don't think that you should learn them as 4 separate formulas. It's sort of silly. They're all the same. So now that you've seen all, I mean, in the textbook you see 4 different types because you see them one at a time. But here you've now seen them all, so you ought to know what the average is. All right. Sorry it's so dark again. I mean, I can't even read it from here, but that's the best I can do. And then finally, there's this business of center of mass. I mean, there's also this business of moment of inertia, but it's sort of, I've never seen any questions on it, so I'm not going to get, particularly from one of the last 2 finals, I believe, has a question on center of mass. So I better tell you about that. The idea is you have and it works for all 4 of these types. You have a density that is given, and it's some function. It's a function that you just write as the Greek letter delta. And so that density is either over this area, or maybe it's over a volume, or maybe it's over a curve, or maybe it is on a surface. But in either case, in any of these cases, it tells you how much the thing weighs per unit mass right near there. So because it's calculus, we don't have to have the same density. A plate can be heavier on one side than the other, and you still might have to work out its mass. So given this density, we have certain formulas that hold for all of them, in all 4 types of integrals. The mass is just the integral, so I'll call it m, is just the integral of, and again, it's whichever type of integral you need, of the density. And it's over whatever that thing is, whatever the object is. So you have to specialize it to one of these types. It's a generic formula that I've written. And then the moments, you have mx. Actually, it's normally written my for reasons that exist more or less to confuse you. This is the integral of x d blah, x times the density. X times the density d blah and the other one is y times that d blah. But you know, those are the moments. There's a 3-dimensional version of it. Rather than worrying about the terminology, I think it's easier to just remember the formula for center of mass. So center of mass, this is the important one. And here it all is, without all these moments. I'll just give it to you as one formula. And since it's sort of low down, again, I'll just read it out to you as well if you can't see it. I'm really cramped. My style is cramped here. You just integrate x times delta d blah over the integral of delta d blah, comma, and then the same thing for y. Y delta d blah over the integral of delta d blah. Is that visible on the camera? Good. And then if there were a z coordinate, you would also, if it's a three-dimensional object, then maybe also a z coordinate, if you need it, which would be the integral of z delta d blah over the integral of delta d blah. And the slanting text has got nothing to do with anything. That's how I could write it. Okay, so if it's a 3 dimensions, you could fit a z coordinate. That's like a possibility, but I haven't seen exam. Actually, there was an exam question from 1993, I believe, that had a center of mass of a 3-dimensional object. So I don't want you to think that you only have a z coordinate, by the way, in the case of a triple integral. In fact, you could have it in any of these integrals except for the area integral. So certainly you could have a z coordinate in a volume. How could you have it for a curve? Well, the curve C could be a contour, a line, or a curve in 3 dimensions. And the surface is certainly embedded in 3 dimensions. So that's a 3-dimensional object, and it would have a z coordinate of a center of mass. So I would put a third coordinate in there for everything but a 2-dimensional object. If it's 3 dimensions, you need that one. Okay, so that's the formula for center of mass, and you just have to specialize it. It's basically the numerator is x times the density integrated, and then y times the density, and z times the density, and the denominator in each case is just the mass, which is the integral of the density without an x, y, or z in front. There was a question.
Yeah, could you just explain what you mean when you say size?
Size? Well, the best thing to understand is if you look at the 4 actual special cases in this example. So if it's an area integral, it's the area. Well, a double integral, it's the area. If it's a 3D integral, it's a volume. If it's a line integral, it's the length of a curve. And if it's a surface integral, it's the surface area. So if a question asks, what is the area of the surface blah? You need to know that you've got to write down a surface integral with a 1 and then compute that. Okay, as opposed to compute the surface integral blah. So it's just one extra little step that says you've got to know to turn surface area into an integral, or to turn length into an integral, you have to be able to realize that that's just an integral with a 1 in the integrand. That doesn't mean it's easy to compute, by the way, as we've seen and will see. Okay, any other questions about any of this stuff? Again, I'm sort of sticking it out front rather than, because it sort of applies to all the integrals I'm going to be talking about today and tomorrow. Was there another question over here? Yeah.
In terms of like finding mass and
center of mass? Yeah.
How is that? How do we do that with surface area? I mean,
Okay, so the question is, how do you define, say, mass with surface area? So you'd be given a density function delta defined on every point of the surface. It would look like delta of x, comma y, comma z equals some function of x, y, and z. And then you'd be given the surface. And that's what's the mass of the surface. So you simply write down, in that case, the integral. It would be a double integral over this surface that was given of delta of whatever the function was, d sigma. And then you have to know how to compute the surface integral, and I haven't told you how to do that yet, and probably won't till tomorrow. Okay? So, but the main aim is to take the idea of a word problem that says a density of a sheet of metal, a twisted sheet of metal in space is given by blah, and the equation for the sheet of metal is this, find its mass. So you have to be able to turn that into an integral like that. I mean, it's not very difficult. You just take the function they give you, stick a d sigma in front, 2 integrals and an s. That's like translating the word problem, and then you have to actually work out the integral, right? But still, it's sort of silly to get stuck by not knowing that the mass is the integral of the density. So all these formulas say the mass is the integral of the density. But what do I mean by integral? It depends which one of the 4 types of integrals we're dealing with. All right? And another question back there.
For the moments, why is it that for the moments the y and the x coordinates are sort of switched over?
The question is, why do I write my and then there's an x coordinate? In fact, if it was in 3 dimensions, then this would be even written as myz. The reason is that it's a moment about the y-axis because the x is the distance from a point to the y-axis.
Yeah, that's where the center of mass.
Yeah, it turns out you need the moment about the y-axis. It's sort of crazy. That's why I say I haven't seen problems that said find the first moment around the y-axis. Instead, I've found find the center of mass, in which case you may as well forget that that you even know what a moment is and just do what comes naturally. The x-coordinate has the integral of x. Sure, when you write out the formula, you have to write my, comma, mx. It's sort of a question of seeing what's not there. So in 3 dimensions, it's yz is the first one, because x is not there. It's crazy. Forget it. Don't worry about the moments. Just learn the bottom formula for center of mass, and you'll be better off. Okay? And that's the intuitive formula. X, Y, Z are in the correct places. Okay, so that's the sort of end of the most general aspect of what I'm going to talk about. Now, everything else is very, very specific, and we'll have lots of examples. So, okay, first big topic is the first one of the integrals that I wrote up that is new to Math 201, double integrals. Okay. It would help if there was a minimum of talking, please. Please. I know I have a microphone, so I can be louder than you. I could be really loud. But it would be very helpful if, nevertheless, since I have to talk for 9 hours just to you for the next 3 days, if you would please not talk while I am. Thank you. Now, by way of introduction, again, to double integrals, let me remind you that you have rectangular and polar. Those are the two sorts. So let's start with rectangular. So you're given a double integral, and you want to set it up like this. So suppose you have this double integral. Now, I want to remind you that some stuff is here. But what is the stuff? If you've got this order in x and dx, dy written in that order, then the dx corresponds to this, the inner integral. And the dy corresponds to the outer integral, okay? So you know this, but it's very important when you look at it to sort of realize this is a nested sort of integral, this inner integral and the outer integral. Now, the bounds of here can have stuff in y. It can be a function of y. But it cannot be a function of x. That wouldn't make sense if there's x things here and a dx. That's no good. So you're allowed to have stuff in y. But once you've done that inner integral, you've gotten rid of all the x stuff, and you just have a regular old integral dy. And so that means that this just has to be a number. So it's a definite integral. Okay, so there's something really fishy if you do not see this. If it's the order dx, dy, the outer integral always just has to have numbers, but the inner integral can have y stuff. Now, of course, if this is reversed, then this becomes x stuff. Okay? Now, how would you go about visualizing or setting up an integral like this? Well, it depends on the region. Now, the principle I'm going to tell you, which you've seen before, about how to do any of these things, is applicable not just to the double integrals, but also the double integrals with polar and the triple integrals in all the different forms. So this is really important to understand how to deal with this. You always start, or at least in my mind, start with the inside integral first. So look at this case, x is the variable, and I want to think of everything else being fixed. Well, here there's only one other thing, which is y. But in a triple integral, there might be dy and dz or something like that. So what I'm doing here is I'm going to say, look, I've got some region here. This is the region that I'm supposed to be integrating. And what this says is I'm going to fix a particular value of y. So I work from the inside. By the way, I'm not going to write necessarily that much of what I'm speaking down, but feel free to sort of take notes that are not just written on the board. Okay, you can look at the video if you want to see the board, but you have to listen or take some regular notes, pretend it's a humanities course or something like that. Anyway, the point is that what I want to do is say fix a value of y. So in your mind, pretend that y is fixed, which means that you're going to mark it on the axis. And then you're going to say, bang, where is the... So imagine a particle that starts way at the left at this height, and then it hits, and it goes out. It's like a bullet. And I want to work out the entrance value of x, x in, and the exit, x out. Okay, that's going to depend on the height of y. For different values of y, you have different ins and outs. And if you're really unlucky, you have multiple ins and outs, in which case you have to split up the integral. But more about that in a second. So basically, this stuff in y is the x in. It's what I call x in. It's the x coordinate where you enter corresponding to that value of y. And the top stuff in y is what I've called x out. It's the exit stuff. So that's the basic idea. If the order is dx, what if the order? So if the order is dy dx, then everything gets reversed. So you look at your region, and you fix your x, and you see what is the height. So now you're firing the bullet up. It's always left to right or bottom to top. And you see what is the y in and what is the y out. And here you have the double integral is going to be from y in to y out. And that's stuff in x. It looks like a y, but of course it's stuff in x because it depends on which value of x. For different values of x, you get different values of this y in and y out, and so that means that it's a function of x, so it's stuff in x, whereas this is now number to number f of x, y, and this time it's dy dx. And again, the way I saw this is I looked at the inner one and I said, okay, there's y, let's keep everything else fixed. In this case, I'm going to fix x, bang, and see where do I go in and where do I come out. Okay, now, what about these numbers? Well, once you've done the inner integral, you still have to worry about the outer integral. And in the case of the double integral, it's pretty simple. All you have to do, let's look at this one. Once you've done this, you've sort of got the hard part done. But you still have to worry about these two numbers. How do you get the outer part? Well, now you start to say, okay, well, I've already fixed y. Now I'm going to, I've done all I need with a fixed y. Now I'm going to let y vary. And so I move the line. What's the first? So y1 as well. So except that there's no variability here. It's just the first y that you need. Below that, there's no x's at all. There's no points. Above that, there's no points. So this number is y1, and this number is y2. Of course, if you're going the other way, you have x1, you have x2. So when you look at it, it looks like a bit of a mess. What's important is not the way it looks there. I've just described a technique. I've just described a technique of how to do it. Anyway, let's try something here. Let's try an example. This is an example from a previous final, although I'm going to extend it a little bit. I'm going to show you a region So here's the region. -2. No, That's not it. It's not that nasty. So this is supposed to be the bottom hemisphere of radius 2. So that's a region R. And the question is to set up this integral. Set up that integral in rectangular coordinates in both ways. You're supposed to do it in both ways. So write this as, so the question would be saying set up but do not compute the integral as rectangular in the form double integral, let's see, dy something dy dx, and 2 rectangular in the form double integral of something dx dy. And the third part is to do with polar coordinates, but we'd come back to that. All right, so this integral f dA means integrate f over this area where f is a particular form. Now, I'll tell you what f is later. The question actually does mention it, but that will be a distraction for the moment. So the question is, how do we set this up in the form dy dx? So I'm going to do the first part. I need to set this up as something, so it's just f dy dx, but I need to fill in these bounds. That's the entire problem, is to fill in these 4 things. There's nothing else to do. Okay, so how are we going to do this? Well, by what I said, you start off by fixing x. So let's fix an x. Here it is. Now all I need to know is where is the lowest part of y? This is the y in. And where is the highest point of y? Y out. Okay, well, y out is pretty easy. It turns out it doesn't matter where x is. It's always y out is 0. You always have a height of 0. So y out is 0. But what about the y in? Well, to get the y in, you need to just know what the equation of y in terms of x. So y equals minus the square root 4 minus x squared. And if you don't believe that, you start with x squared plus y squared equals 4, which is the whole circle. And then you solve for y, noting that you need the negative square root, not the positive square root. So here I have minus square root 4 minus x squared. So that's the y in. All right, now I just have to worry about the x. So I say, okay, where's the first x when I actually hit the region? Minus 2. Where's the last x? 2. So there is the integral. I've set it up. You don't need to write this equals y in, equals y out. That is, I'm just writing that for reference now. Okay? Any questions about what I just did? Okay, well that was fairly straightforward. How about the other way? Again, I need to set it up, but this time it's dx dy. And to illustrate the new approach, I pick a y instead, and fix like that. And I say, where is the first x? And where is the last x? This will be x in, and this will be x out. Okay? So, again, I've got to use the equation. Here, however, I'm going to solve for x, and write x is plus or minus the square root of 4 minus y squared. Notice that this time I solved for x, but I couldn't decide whether it was plus or minus, because the x in is the minus, and the x out is the plus. But that's exactly what I need. The x in for a fixed y, again, I'm sort of fixing y because it's on the outside. The x in is minus the square root of 4 minus x squared, and the x out is plus the square root of 4 minus x squared. And now we just have to worry, where does y start? Well, minus 2, and it goes up to 0. Okay. Any questions about this second one? Okay, let me just tell you something about this. If you look at either of those double integrals as a given, we've worked them out from the region, but if you looked at them as a given, you would be expected to reverse engineer them into the region. So what I'm trying to say is, starting with the geometry, you have to go back to the algebra, but you're also expected to go from the algebra to the geometry. Okay, so the question is, how do you reverse engineer it? Well, forget that you knew the picture of the thing. Yes, thank you. These are y's. With all that phone kerfuffle, I made a mistake. So please convert them back. Yes, in fact, if you do see x's with respect to the dx integral, you know that there's a mistake. It just doesn't even make any sense. So yes, please make that change. Okay? Now, what I'm trying to say is, starting at either of those integrals, you'd be expected to be able to reverse engineer it. And the way you can do that is exactly the reverse of what I said. Suppose you start with the top integral there. You say, oh, well, I know that... So take this top integral. What it says is, for a fixed value of x, we know that minus root 4 minus x squared is less than or equal to y is less than or equal to 0. And x is between minus 2 and 2. Okay, so what you have to do is draw the graph of this. And the graph of this is exactly that. You draw these two curves and take everything in between. And then that's the full region of x. If x had gone from 0 to 1 only, you would only have this section. That's from x from 0 to 1, as it turns out. But since you're going from minus 2 to 2, it's everything. So what I'm trying to convince you is that as you study this thing and as you do practice, make sure you do some of the problems, or try to find some of the problems that say, you know, here's the integral, now reverse the limits of integration, or what region does this correspond to, sketch the region. That sort of question is what you're looking for as well. Okay, so any questions about the basic, well, about that example? Basics of double integrals. All right, let's talk about polar form. So polar coordinates, as you know, you have to know that x is r cosine theta and y is r sine theta. That's absolutely important. And of course, along with that, is the formula that you should just be aware of, that x squared plus y squared equals r squared. That, of course, follows from the above, but the last thing you want to be doing is applying trig identities for something as basic that should be ingrained in your memory. So given this transformation, the basic idea is that instead of dx dy, you replace this with, not with dr d theta, but with r dr d theta. That's very important that you don't forget that. That's effectively the Jacobian of this transformation. Now, in terms of the computation of such a beast, so we're going to try to set up this integral stuff f times r dr d theta. So what this says is we have a fixed theta. I'm fixing theta first. So by the way, it is possible to reverse the order here, but it almost never comes up in applications. It's very rare to have it in d theta dr. The r just, by the way, belongs with the f in the end. So you would reverse these two, but I've never seen a problem involving that. But on the other hand, in this order, you have some region. I don't know, whatever it looks like. The difference is we're fixing theta, and theta corresponds to a ray from the origin. So you always start at the origin, and you go whizzing off along a certain direction, theta. And just to remind you, theta is always measured, as is conventional, down to the positive x-axis, and typically between 0 and 2 pi. Although here you don't necessarily need all of it, but more on that in a second. So instead of firing the bullet from left to right or from bottom to top, I'm going to start at the origin and fire it along here. And I'm going to see where does it go in and where does it come out, as usual. But this time I'm concerned with the distance from here to here. That's r in. It's the value of r where you go before you get into the thing. And similarly, I'm also concerned with r out. So this is r out. So I don't care about the x and y coordinates. I only care about the distance from the origin of the bullet when it goes in and when it comes out. And again, it's different perhaps for every value of theta, or it's conceivably different. If it's a circle, it's the same as it turns out, but for more complicated things, it could be different. So again, r in, well, I'll write this integral as r in to r out, and these are both stuff in theta. They're functions of theta. It depends on the angle, perhaps. And then finally, we need a number, and what you do is you find the first value of theta, the lowest value, so now I hit. Then you keep going, and this would be the last angle. What do I call it? Theta 2. Okay? So, let's do a simple example, and then I have a few more complicated examples. Well, maybe I don't. I have some more complicated principles. Now, let's take this previous example on the right-hand board and write it in polar coordinates. Okay? So, the question is to take this region, I'm going to pull this down now, take this region and write it in polar coordinates. So this region from before in polar. Okay, let's apply the principle. I'm just going to draw the region again. This time a little bit smaller. So I start here. It's pointless going up because if theta's anything between 0 and pi, actually you don't get anything. You're not in the region here. So let's take theta like this. So this is, I'll label this as theta, but actually it's this angle here, which is theta. And I say, okay, I start at the origin and I move along. I fire the bullet. When does it go in? Well, it goes in immediately. So r in equals 0 because I'm immediately in as soon as I start. And I get out at 2. It doesn't matter which theta I'm at, as long as I'm in one of these acceptable ranges of theta, I always get out at a distance of 2. The distance here is 2 because it's a circle. So in this case, these are constant functions of theta. Okay? So now, then, you go like this. Theta goes from, well, the first value is pi, and the second value is 2 pi. Okay, so 0 pi, that's when things start getting interesting, and you actually encounter the region, and you go up to 2 pi. So the integral we're looking for is this. It's the double integral. Well, I'll write it. It's the double integral of f times r dr d theta. R goes from 0 to 2, and theta goes from pi to 2 pi. Okay, that's exactly the same integral as either of these two. It's the same integral. And the actual question Now it is time to tell you what the actual question was, because we've already done most of it. The question said, it gave it to you in this form. It said, consider this integral. The integral from -2 to 2 well, this is my adaptation of the question anyway. I forget exactly what it said. 1 over, what's my version of it? 4x squared, was it? No, 1 plus x squared plus y squared. dx dy. dy dx. Is that right? No. No, they had it in this. Well, whatever. That's what I'm going to say the question is. This is a slight variation of a final exam question that I got from the website. Here it is. It said, consider this double integral. Convert it to polar and solve it. The question was to take this and convert it to polar coordinates. And the way you're going to do that is, first of all, to reverse engineer it and realize, hey, y is between this curve and this curve, as I said, and x is between there. So you have to draw the curve, then do the polar trick, and realize that this needs to be converted exactly as I just did. I'm not going to redo it. We found it was from between pi and 2 pi, and r between 0 and 2, 1 over something or other, r dr d theta. Now the problem is that you want to put x here. You want to immediately convert x squared plus y squared into r squared. If that's not so obvious, you at least want to change x into r cosine theta, and y, again, is r sine theta, and you could just do that and drop that in place, remembering to square both of them, and then, of course, realize that cosine squared plus sine squared is 1, and you reduce it to this. Now, this integral is fairly straightforward. Throughout, okay, I'm supposed to do the inner integral first. I'm supposed to do that inner integral first, and then do the outer integral. But I can already see that the inner integral is not going to depend on theta. I can already see that because there's no theta stuff here. In this example, the r was r in and r out were constant functions of theta. So the beauty of this is you can actually do this. It's not going to depend on theta, so it's a constant. You can literally bring it outside the integral. So you can just write this as r over 1 plus r squared dr times just the integral from pi to 2 pi d theta. And frequently I will do that without much comment. It's very frequent that you can do that both in polar and also in cylindrical and spherical coordinates for that matter. Okay, so this only works because this does not depend on theta. It's not necessary to do this, but it saves a little bit of time, actually, in a way. So the deal here is that if this stuff had theta in it, which it could, this would be illegal. This is no good if this stuff, in particular, does depend on theta. Okay, so anyway, these integrals are very easy. First one works out to be 1/2 log of 1 plus r squared from 0 to 2. And the other integral is just 2 pi minus pi, which is pi. And if you work this out, because log 1 is 0, you will get pi over 2 log 5. Okay, any questions about that example? Okay, so the third technique that you have is a sort of extension of the polar. It's a general change of variables. So the third type, polar should have been number 2, but I probably left it off. 3, change of variables. So the deal here is that if you can do a substitution of the form x equals something in u and v, or whatever variables you like, we just use u and v, and y is other u and v stuff, then you can change the integral with a simple principle. You just replace everything appropriately by u and v, but you need to change dx dy has to change into something more complicated. It's the absolute value of j du dv. You replace the dx dy by that weird quantity. What is the absolute value of j? Well, j itself is the Jacobian, which is itself a determinant of a 2 by 2 matrix that is essentially dx du, dx dv, dy du, dy dv. That's the entire theory of that without any justification of why it works. I'm getting quite practical here. You've got the exam coming up in just a few days. I would love you to know why it works, and hopefully you saw some sort of explanation of what's going on in terms of changing areas and segments and all that. But, you know, at this point, well, the cynical, practical me, part of me says, just show them how to do the damn question. So that's what I'm going to do. That's what I'm going to do. All right, so here's a question. Find the area, an example, inside the curve x minus 2y all squared plus 4x plus y all squared equals 1. That's some bizarre curve that I'm too scared to draw. Okay, I don't know what it is. It's some conic, an ellipse of sorts, but it's probably all turned and distorted and all that sort of stuff. So find the area inside that. We're going to call this region R. I hereby dub the R. Okay, so whatever the region looks like, I'm going to have to find the area inside it. So the first thing I have to realize is that what I'm looking for is a double integral of 1 dA, or dx dy if you like, of R. So area, you just set up an integral with a 1 in the integrand. Okay, but this situation is absolutely rife, whatever. We want to change variables into something that makes it much more familiar. So if you look at it, it looks almost like a circle. It almost looks like a circle. So what do I want to do? Well, let's say I call this u. So let's say I call u equals x minus 2y. And I'm going to be a little sneaky and think of the 4 as a 2 inside there. So I'm going to call v 2x plus 2y. If I do that, then this is just u. So this becomes u squared plus v squared equals 1. This is the transformation of the region into these u and v coordinates. Right? Because v squared is 4x plus y all squared. 4 outside of x plus y all squared. The 2 gets squared and you have x plus y. Okay, so it didn't tell you to do this, by the way. The question was as I stated it. But you sort of have to think variables is a good idea, and this is a good change of variables. So that's the sort of tricky aspect of this problem. But you can see that you'd much rather deal with that than with this. All right. So now we have to find a Jacobian. But you might remember, or if you don't remember, you can look at this board and see it, that you want x in terms of u and v and y in terms of u and v. Whereas over here, we have u and v in terms of x and y. So we have to solve for x and y. And you better hope that there's only one solution, as in that you can invert this problem, or else this technique becomes much more complicated and you have to break things up and blech. Okay, so let's do it. And then I think we probably have to take a break. Okay, here goes. All I do is add these two equations, and if I do, I find that 3x is u plus v. So add them to get 3x equals u plus v, i.e. x is 1/3 u plus 1/3 v. Whereas if I now say plug that in, I see that, so in the first one, I have u equals 1/3 u plus 1/3 v minus 2y. So 2y equals minus 2/3 u plus 1/3 v. And so I'll just summarize the situation as x is 1/3 u plus 1/3 v, and y is equal to minus 1/3 u plus 1/6 v. That's what you get when you solve the two. And that's pretty nice. For every value of u and v, there's only one value of x and y. Okay, so I just solved these linear equations. Now I've got to find the Jacobian. So the Jacobian is the determinant of this 2 by 2 matrix. So I need dx du, which is 1/3, no matter what u is. Dx dv is also 1/3. dy du is minus 1/3. And dy dv is 1/6. So to compute this Jacobian, I take the determinant is 1/3 times 1/6, which is 1/18, minus 1/3 times minus 1/3, which is minus 1/9. If I work that out, it's 3/18, which is 1/6. And it is not even a function of u and v. It's a constant function of u and v. Anyway, so just coming over here, this integral is equal to the integral over the transformed r, nu r, in u and v land, of 1 times the Jacobian times du dv. It's actually the absolute value of the Jacobian, by the way. I just want to point out one thing. Over here, when I put this absolute value, it looks like absolute values. Think of them as just big vertical lines. This is a determinant, not an absolute value at all. This is a determinant. You could come up with a negative answer. Absolute values are not negative, but determinants are. It's just an unfortunate duplication of notation that uses big vertical lines to mean determinant for a matrix. So this is a determinant det. Sometimes people write det of a matrix instead of the absolute values. And then once you've found it, you should get a number, or at least a function of u and v. This is an absolute value, so you have to take the absolute value of it. That's actually an absolute value. So just to clarify, you have two sets of double lines. One in the actual determinant and the other is the absolute value. Anyway, so the nu r in this case, as we saw, is u squared plus v squared less than or equal to 1. And the Jacobian is 1/6 in the absolute value of that, which is, of course, just 1/6. And so don't worry about the 1/6. This is a double integral. But there's no need to compute it. You just have to recognize that it's just, apart from the 1/6, which is just a constant anyway, this is the area of a circle radius 1. And we don't need calculus to work that out. We know it is just 1/6 times area of circle radius 1, which is pi times 1 squared, so it's 1/6 pi. And that's the answer. A question?
On the exam, when there's things like that where you just use geometry to figure it out and not have to use calculus, can we do that? Like, will we lose points?
So the question is, would you lose points for changing this into this, essentially, by just using geometry? Well, if it's just the area of a circle, no. If it's something more complicated and exotic that you happen to work out, like you happen to work out this question, and you said, oh, well, in review session we did this, and I remember it's the same question, and the answer is pi over 6. Well, I mean, that would be bizarre, of course, to just reuse the question, but you never know. I'm not setting the final, so you never know. You might look back and say, oh, no one will remember that. And I don't consider it acceptable then to say, yeah. But I mean, if it's just a circle, and you write 1/6 times area of circle of radius 1 like I did, then it's very clear you understand it, and yes, that's a standard formula, and you're encouraged to think outside the box in that sort of way. So it would be better to do that than just to write the answer without indicating how you got it. So if you are going to use geometry, write a few words about how you used it and be reasonable about it. So what we've actually done is, whatever this distorted thing was, it was some sort of distorted ellipse. We wanted the area of that. What we did, okay, come on, we're not taking the break just yet. This is xy, this is uv. What we did was sort of apply a distortion filter to change it to this. And what the Jacobian says is, for every square here, that corresponding distorted only area 1/6 as much. And so whatever the area of this is just somehow you have to magnify this to get from here to here. You have to shrink this. So I guess this is expanded by 6. So in one direction it's 1/6, and in the other one it is 6. Okay. All right. So this one says use a substitution to find a particular double integral. Again, this is a final question. All my examples essentially come from previous finals, or at least adapted from it. So here goes. Actually, I had a few more things I wanted to say about double integrals, which I will do after the break. So it says find this, where I have to tell you what R is. R is the interior of x squared over 4 plus y squared over 25 equals 1. All right. So it's the integral of root 25x squared plus 4y squared. Okay, so it suggests that you use a change of variables. So in order to do this, we're going to, instead of using u and v, I think it makes more sense to use r and theta. See, this is almost a circle. If it was a circle, you'd just use polar coordinates. But because it's an ellipse, you're going to use modified polar coordinates. So what I want to do is set up, in terms of r and theta, I'm going to simply let x is equal to 2r cosine theta, and y is equal to 5r sine theta. So it's modified polar coordinates. The reason I choose the 2 is because when you square it, you get 4, and that cancels out the 4. And when I square the 5 here, I get 25, which cancels out the 25. It helps to have seen it before, of course, but you can see intuitively that instead of r cosine theta, we stretched out the x in the 2, and we stretched out the y in the 5, and that's very well, because if you actually draw the picture, it's an ellipse like this. That's exactly what we want. Anyway, the beauty of this is that if you plug this in, which I will now do, actually let's do the Jacobian first. Here I do not have to solve for x and y, unlike in the other example, because I already have x and y in the nice form. So the Jacobian, I'll write it out in full. It's the determinant of dx dr in this case, dx d theta, dy dr, dy d theta. Which now, specifically, dx dr is 2 cosine theta. Dx d theta is 2 r sine theta, but don't forget the minus because it's cosine. Dy dr is 5 sine theta, and dy d theta is 5 r cosine theta. By the way, I completely forget whether you're supposed to write dx dr, dy dr, and then dx d theta. You can switch those two around. It doesn't matter when you compute the Jacobian because it's just this times this minus this times this. And as long as you have these two right, it doesn't matter which order this is in. So my apologies if I flip them around.
What about the order of dr
that matters. That has to be in this order if that's in that order. But you can swap both of those and those. There's no preference between r and theta. You just have to be multiplying this times this minus this times this. And if you do, you find you get 10r cosine squared theta minus sine squared theta. And you get 10r. And so coming over here, this is equal to the new r, which I will specify in a second. 25x squared is 2r cosine theta all squared. Oh, hell, there's no room. Okay, never mind. Plus 4 times 5r sine theta all squared. And then I'm going to have to squeeze this in, but on your page you should put this here. And then you have to have the Jacobian times dr d theta. Okay, so we have to do a little bit of work, but we're almost done. What is the new r? Well, if you plug these in, you find that r here goes from 0 to 1. So we should have specified also that r goes from 0 to 1 and theta goes from 0 to 2 pi. Well, it's basically polar coordinates, except that clearly when r is 1, you get x equals 2 cosine theta, y is 5 sine theta, and that's the actual boundary. When r is less than 1, you get somewhere inside. And theta has to go from 0 to 2 pi, of course, so that you get the entire thing, times the integral from 0 to 2 pi, the integral from 0 to 1. We have a square root of r squared, another r, so we have r squared dr d theta. And I'll work this out very quickly as follows. First of all, this doesn't depend on theta, so I'll do the same trick, 0 to 2 pi d theta, which is just 2 pi. The other one is r cubed over 3 from 0 to 1. And so you get 100 times 2 pi times a third. In other words, 200 over 3 pi. So that's the area. Well, that's not the area, that's the value of the integral. I know we've only got a second of tape remaining, but are there any questions about that?
Where did you get the R bounds?
How did I get the R bounds? Well, yeah, I kind of rushed through it. How did I get the R bounds? Well, capital R is the interior of this. And I asked myself, well, what is the actual curve here? It's x equals 2r cosine theta, 5r sine theta. If you plug these values in, let's just do it explicitly. Plug these values in to this equation, and you will see you get 4r squared cosine squared theta over 4 plus 4 plus 25r squared sine squared theta over 25 equals 1. And if you cancel out the 4's, then you'll see that r squared equals 1. So just by plugging it in, you get r squared equals 1. Yeah?
Are we just like simplifying an ellipse into a circle?
Yeah, that's all this is. We've changed an ellipse into a circle, but then we've used polar coordinates to change it further. So it's, you could think of it as a squish into a circle of radius 1, followed by polar coordinates, but we've done them in one step. Okay, if you didn't have these numbers out front, then you wouldn't have 10r, you just have r. Another question. We haven't taken a break yet. Please, give me another 2 minutes, and then we can talk to your heart's content.
Do you have any general recommendations for how to do substitution?
It's very difficult to come up with a general recommendation of how to do a substitution. That's essentially what the question is. How do you do it? The fact is, even in one variable, it can be difficult to find a substitution. 2 variables, really difficult. The basic idea is to try to turn the region into something that you know. In both of these examples, we've changed whatever region it was into a circle. There are other examples where you change it into a rectangle. But if you can change the region, then things turn out to be a lot simpler. Of course, sometimes this becomes a mess as well. So in general, it's probably whatever you try will probably be wrong. You have to be very lucky to have a proper substitution. But on the other hand, these problems are sort of constructed so that you're lucky. I mean, how lucky was it that this integrand happened to be exactly this thing times 100. That's why it worked, right? I mean, this is the curve. Why the hell should you be wanting to integrate that function over this inside this curve? I mean, it's just like they happen to be magically compatible. Then again, in real life, problems that come up, sometimes you do find magically compatible things. But on this exam, if it's something that looks nasty like this, I would say either try to change it into a circle or a rectangle. Make a substitution. All the other problems that I saw, by the way, told you which substitution to use. These are the only two that I found that didn't. So I did them because they looked hard. There was another question taken. It's been retracted. No, there it is. So the question is, where does the extra r come from in polar? Okay, so the question is, in polar, you know you need the r. What happens, why didn't I need an extra r here? And the answer is I'm not doing polar, I was doing my own substitution that happened to look like polar. These are not polar coordinates, they are polar-like coordinates. And I've already got there's the r of the polar coordinates. Now, to make this more precise, imagine you tried to do polar coordinates but using the Jacobian method. So you forget that you know what the dx dy changes to, you just want to use the Jacobian. If you did, you'd find you get exactly the same thing without the 2's and the 5's. So you would get r dr d theta. And so then that's all you would use. And you don't need the absolute value of r because r is positive. So it's a mistake to put an extra r because that r in polar, the r dr d theta, is the red Jacobian. So the two methods are the same. It's just, you know, you can do the polar without knowing Jacobians. All right, so let's take a break now. Before I move on to triple integrals, here are a couple of little tips for polar coordinates that I kind of forgot to mention. Actually, before I even do that, I've got to say one thing. Suppose you have a double integral of stuff dx dy. Okay, so in my previous version, I said we're going to fix y and we're going to sort of break it up. So suppose your region looks like this. Okay? Well, no problem. No problem. What I do is I fix my y and I compute my x in and my x out. And that's going to be pretty straightforward. But suppose that I did this same integral dy dx instead. Then forget that. I'd have to fix my x and work out my y in and my y out. Now the problem here is that although the y out is very easy to deal with, the y in, there appears to be two different sort of paradigms. One for this range of x and one for this range of x. So there's sort of, I break this up. If you are determined to do it this way, you want to break up the region into two pieces and do two separate double integrals and add them up. Because you'll have two different formulas for the x, for the y-ins and the y-outs. Okay, so that's just one comment that you might need to break it up. And we'll see a couple of examples in triple integrals, so I'm not going to dwell on this. But given the choice for a region like this, you would much rather do this one, dx dy, than this one, dy dx. Because this one, you can see for a fixed x, there's two different functions for the bottom part of it. Whereas here, for a fixed y, there's only one function from the bottom, which is the left in this case, and one function for the top, which is the right. Okay, so this is preferable for that particular shape of region. On the other hand, there are shapes where you may not even be able to avoid either direction. You might have to split. I mean, if the thing looked like this, if you did it in terms of this dx dy, so you fix y, there's two different y regions. This is one, and this is the other. Here, the bottom's the same in both cases, but the top, as in the rightmost part, changes, so you have to split. Whereas if you did it the other way, you'd be splitting it along there. And again, the bottom, well, this time the bottom is different. So if you do dy dx, then the bottom there is different from the bottom there. So you may have to split up into two. couple of other tips about polar coordinates, which, by the way, can also be used in cylindrical and spherical coordinates, which we'll do in a bit, is sometimes your region is not a nice circle as in centered at the origin, but might look like this. Suppose this is your circle. And let's call this, say, 2. Let's say that's 2. Okay, so I say pick a theta. I'm going to ask you to describe that region for polar coordinates. So I say pick a theta, and I say, okay, fire a bullet, bang. Well, it goes in at 0 immediately, but where does it come out? We need this length r in terms of theta. So you need to do a bit of geometry. We need r as in the out r in terms of theta. Okay, so how do you do that? Well, you use a bit of trig and circle geometry. The real trick is to do this. Draw this line in. And then the angle in a semicircle is right. And this is the radius, or the diameter actually, which happens to be 2. So in this picture, that's theta. This is pi over 2 minus theta, as in 90 degrees minus theta. And so this is also theta. Now we can do it. In this triangle here, sine theta is r over 2. In other words, r is 2 sine theta. And this is r out. R in is 0. And now this is a function of theta. So your double integral in polar coordinates is like this. Whatever it is, r dr d theta as usual. But now we're going to go from 0 to 2 sine theta. That's r in to r out. And in this case, you also have to go and ask, what's the first theta? Well, actually, theta equals 0 is the first theta, because as soon as you move, no matter where it is, because this is tangent, even the small theta, you will be in the circle a little bit. So 0 is the bottom, and then you keep going until you get to pi. And that's when you get out. Okay, now I want to emphasize that my little trick of I just pulled them apart because I noticed, you know, that it would work. Will not work here. Why will it not work? Because of this. No split. That inner integral, when I do it, it'll have r stuff, whatever, theta stuff. This will have theta stuff. And so that actually has to be integrated. You cannot just pull it out and split them apart. Okay, so I don't want you to get the impression that in polar coordinates you can always split it apart. So anyway, that's the sort of example. A question first.
What would you do if you had a circle like that, but it wasn't touching the origin? Like it was off the axis?
If it was off the axis, you have to use the cosine rule, and it's a royal pain. We can, if you have a question like that that's specific, and I believe there is one in one of the previous finals, we're going to have to do that on Thursday. Or you can show me afterwards, or, you know, I'm happy to show you before. I don't really have time to deal with such exotica right now. Okay, so there's an example. Just in general, try the angle inside the circle being right, and that should help. That same thing works if the circle's on the x-axis. Okay, so that's the end of double integrals. But again, a lot of that stuff also applies to triple integrals. Okay, so are there any other questions about polar double integrals, anything like that before I move on? Oh, yeah. Oh, I didn't mean I had general tips. I mean I had a few extra little tips or things. So here they are. That's them. You've just seen the general tips. Okay, but again, now that I have done double integrals, it turns out triple integrals are not so bad. So I will show you the theory of it, but then I have a bunch of examples that I want to deal with. So, of course, in some sense, the triple integrals are the bad ones, and the double integrals then become much easier. But the principle is the same. So triple integral. Okay, so suppose I have a triple integral like this, something f, and let's do it in the dx, dy, dz order, just to start off with something. Okay, so I've got some region R, a domain of space, I don't know what it's called, I don't know what letter to use. It looks like this. Here's y, here's z, here's x, and I have a certain blob in space. Okay. pick the inner integral, which in this case happens to be x, and ask, what happens if I fix y and z? So this means that I'm picking a particular point, in this case, in the yz plane. Bang. And I take a line parallel to the x-axis. So this is a line of constant yz. And I have to fire the bullet. In this case, x is getting bigger going that way. So this will be some x in, and this will be x out. Now that's sort of hard to visualize. So in the interests of sanity, let's forget that. And let's do something that's easier. Although you may have to do that. But for illustrative purposes, I'm now going to backpedal and, or at least change it to this version. Same sort of region, but maybe this will be a little clearer. So I have some blob in space. This says fix a particular value of x and y. So I'm going to pick a value x, comma y here. And I'm going to let z vary. So this time I'm going to fire the bullet up. And then this, wherever this hits, and it's sort of hard in 3 dimensions because it could actually be going underneath this ball and coming out on the other side, whatever. Wherever it hits, z in and z out. So I'm going to fill in the z in and z out. And again, z depends on both x and y, the z in and the z out. So these are both stuff in x and y, but not in z. So the inner integral, if it's dz, then the bounds can depend on x and y. Okay, so then the next thing to do is to say, okay, which x and y's are acceptable? Which x and y's are acceptable? Well, if you imagine a shadow going down, you're going to have to try to geometrically identify this region here. This is the shadow of the ball or whatever this lump is. And then you just do a double integral, the same thing. Next you fix, in this case, you fix x. You always fix the outermost thing. Remember, we started with fixing x and y and found the z bullet. Here, I'm going to now fix x, which is, here's the x-axis. And I see where is the y in and where is the y out. So this is the y-axis. This is the x-axis. This is the z-axis. So I fill those in. Y in to y out. As usual, only stuff in x. And then finally, I find what is the first value of x and what is the last value of x. So these are actually x1, the first value, and x2. So x1 to x2. And those are just numbers. I'm not going to clutter it up by writing the word numbers there. All right, so that's the basic technique. Bless you. All right, so rather than do examples yet, I'm going to show you both cylindrical and spherical coordinates, and then a lot of the examples involve all three, so it'll be a good way to review at this point. So cylindrical coordinates look like this. Cylindrical coordinates, first of all, you need to know what they are, but luckily they're just polar coordinates in the x and y, so we already know that. And the z doesn't do much, it's just z. It's just z. So you need to know x is r cosine theta, y is r sine theta, and z is z. Now it's very important to get a sense of the geometry of the thing. So if you're going to use those coordinates, then you have to be aware that you're just using polar coordinates in the xy plane. So r is this distance here. So if you have a point, r is the distance from the z-axis, no matter how high you are. So r equals distance from the z-axis, not from the origin. Geometrically, r is the distance from the z-axis. So wherever you are, you just find how far it is. And then theta is the angle around, actually, if this is the x-axis, and this is the y-axis, then you always start at the x-axis. So theta is the angle in the xy plane. Okay, so again, we'll see some examples. The important thing to know for cylindrical is that dx, dy, dz gets replaced by one of the following forms. R dr, well, let's do this one. dz times the polar form, r dr d theta. Or it can be written as r dr dz d theta. Actually, maybe I better do some cylindrical example before I do polar, so we can just work out how these things, these bullets, or whatever you're thinking of them as, are going to tell us where things go in and out. So before I do spherical, a little cylindrical. So actually, I'll do both. I'll do both of the things so far. Okay, here's a problem. So it says, consider the sphere x squared plus y squared plus z squared equals 4. And what's more, I would like to have z between 0 and 1 only. Okay, so let's draw that. Well, I didn't draw the bottom half of the sphere because already I knew that z only had to go from 0 to 1. Actually, the sphere has radius 2, but we don't need the top of it. So maybe I've got to dot this at the top. Sorry, what's the question?
What was the problem here?
Well, I'm getting there. I'm getting there. So it says consider this, okay? So we want the region inside the sphere. In fact, it was probably even written as less than or equal to 4 to indicate we want the interior, but we only want the z going from 0 to 1. And the problem is to find the volume of this. Find the volume. Okay, but we want to be able to do it in all sorts of different coordinates. So the problem is to find the volume, at least set up the integral using rectangular, and then also we should set it up using cylindrical and then spherical. So I'm not going to do spherical yet because I didn't tell you what they are. I decided to pop the example in here after the first two. Okay, let's do rectangular first. So we need to pick an order of integration. We need to pick an order of integration. And I somehow feel that although there might be some utility in doing it in a certain order, I kind of feel right now like doing the z first. So let's suppose the problem was this. I'll give myself plenty of space. It's a volume, so the integrand is 1, as I described earlier. So you're going to have, I want to do it as dz, dy, dx. I'm going to demonstrate two ways of doing this. One is geometric, and the other one is algebraic. So first of all, geometric. Here's z, right? That means I'm going to pick x and y. Bang. And I'm going to draw up and say, where do you get to? Well, I have an in and I have an out. But the problem is if I start out here, then the out is different. Here it hits this flat top, whereas there, the out hits the curvy bit. So it's sort of complicated, but I felt like doing it this way, and I'm going to stick with my gut, even though it's pretty nasty. Okay, so here goes. I want to distinguish, this height here is 1. This z height is 1. Okay, if I'm determined to do this problem in rectangular coordinates, I need to work out what is the shadow of this. So this height is 1. What is this radius? What is that radius there? Well, sorry, that height is 1. This radius here is 2. This is 1. So this is root 3. So if I cast a shadow, the shadow of this region in the xy plane looks like this. Here's the xy plane now. I'm going to have a circle of radius root 3, and then another circle of radius 2. So this is like an overhead view of this object. The interior circle is the flat top projected, whereas the curved surface is here. So clearly this is a pretty ugly thing, but we can do it. We can do it. Okay, so what I'm trying to say is already we have to split this up. We already have to split this up. So for fixed x and y, if x and y are between, it lies within the circle of radius root 3, namely if x squared plus y squared is less than or equal to 3, that's circle of radius root 3, then z goes from 0 to 1. So we've seen that geometrically. If we're inside here, then z starts at 0, and it's at the top flat bit, which is at height 1. But if, on the other hand, x squared plus y squared is in this exterior part, which is 3 less than or equal to x squared plus y squared less than or equal to 4, which is 2 squared, then z goes from 0 to something. What is that something? Well, that is the curved surface. And the curved surface is, you come back to the equation over here, and you have z squared equals 4 minus x squared minus y squared. So it's root 4 minus x squared minus y squared. Yuck. But nevertheless, that's what you have to do. Now, this is if you use rectangular coordinates. In that order, dz, dy, dx. Okay, but we will find that some of our work will get to be reused anyway. Now, the thing is, how do you parameterize x squared plus y squared less than or equal to 3? Well, let's not worry about the curved bit. Let's just worry about this interior bit. And we see that now the next thing we have to do is fix x and work out where is the in and where is the out. Well, this curve here, this circle, is given by, in this case, y equals plus or minus root 3 minus x squared. So basically, in here, we have y from minus root 3 minus x squared to plus 3 minus x squared. Unfortunately, for the other circle, we have an absolute mess. And the reason we have a mess is because it's different from there to there. So actually we'd have to split that up into 3 further integrals. Okay? So I am not going to dwell on it. The inner integral goes like this. So we're going to end up with 4 total integrals. The answer looks like this. Okay, so for the inner integral, the z went from 0 to 1, and the y just goes from minus root 3 minus x squared to root 3 minus x squared, whereas the x coordinate goes from minus root 3 to root 3. It's always dz, dy, dx. So that covers the interior part. Now let's deal with this part. So from here, I've decided against doing a second method because it's too long. From here, we're going from x going from minus 2 to minus root 3. Y goes from this bottom curve, which is root 4 minus x squared with a minus up to root 4 minus x squared. And z this time goes from 0 to root 4 minus x squared minus y squared. And that's, again, 1 dx, dz, dy, dx. So that's now covered this section. As for this section, let's now deal with this section. So there's another one just like it. Same thing. I said I wouldn't write below here, but I've got a cheat. Same thing. Except this time we can root from 3 to 2. And then the others are the same. Minus 4 minus x squared up to root 4 minus x squared. And then the z goes from 0 to root 4 minus x squared minus y squared. 1 dz dy dx. Unfortunately, I have to come back and do the rest of it. But even that I'm going to have to break into two pieces. Because for a fixed x, I have an in and an out and an in and an out. So I've got two more bloody integrals to deal with. Okay, so the first one is from minus root 3 to root 3 again. This time, let's do the top half. The y comes in at the bottom curve and goes out at the top curve. So the bottom curve here is root 3 minus x squared, and the top curve is root 4 minus x squared. And the z, again, always from 0. I know this is boring, but you have to bear with me. And finally, the very last one is the bottom piece, which goes from minus root 3 to root 3. That's the x range here. And then the bottom of these curves is minus root 4 minus x squared. And the top curve is minus root 3 minus x squared. And then always, this is the ta-da! Okay. So there is a rectangular coordinate version of this damn thing. A question?
Because you're using the addition of integrals, couldn't you say that the integral that's excluded from the hemisphere, volume of that plus the included volume sums to the volume of the hemisphere?
So a cleverer way might have been, indeed, to find the whole volume of the hemisphere minus the cap part. And then you could write it as a difference of two integrals. And it occurred to me as I was writing all these integrals that that might be a better way of doing it. But on the other hand, I thought I'd better play Pat and show you exactly the method that I described, as in the bullet method. The other one is like a virtual bullet. It's a negative method, which would make a lot more sense. However, none of these methods makes much sense, because what you really want to do is cylindrical coordinates. So, let me tell you what the, let me tell you what, well, okay. Let me erase the board, then I'm going to tell you. Let's reapproach this problem using cylindrical coordinates, because that was a mess. Okay, here goes. In cylindrical coordinates, let's do this as follows. Let's try to write it in the form 1. And remember, I said there were two forms of this. So if you do it in this form, dz, r dr, d theta. Let's try that. Now I have to tell you, this is exactly how the solution in the official solutions does this problem. So what they say is they say, here's x, here's y, here's z. What we're going to do is we're going to fix our r and our theta. And we're going to say, what is the height that you go up to? Well, what I'm saying is, pick a point on the xy plane. It has coordinates r and theta. So you should be good at drawing that. Sorry, this is the x, this is the y. This is level. Okay, so notice that you have to sort of tilt your head around and say, oh, there's the r, and the theta goes down to the x-axis. Okay, and then the question is, fire a bullet up again, and where is z in and where is z out? And we run into exactly the same problem that we did in the previous integral, in that it depends whether r is less than or equal to something or greater than or equal to something. But nevertheless, This is the idea. Again, if you have to realize that the inner circle, it's the same picture as here. The inner circle goes up to root 3, and the outer circle goes up to 2. So this inner circle is root 3, the outer circle is 2, and so we're actually going to have to split it up into two integrals, but they're not as bad. They're not as bad. So the first piece of geometry is this. If r is between 0 and root 3, then we're in this inner circle, and the height of z is 1. But the beauty is that theta just goes from 0 to 2 pi because you need the entire revolution of the thing. The theta, every value of theta is possible. So r is going to go from 0 to root 3, and z is just going to go from 0 to 1. Now, the other part of this picture, theta is no problem, is what happens when r goes from root 3 up to 2. So let's look at it. Let's look at it. When r is over here somewhere, the question is, how high are you? How high is z? Well, there's a triangle. It's r, z, and this is 2, because this is the sphere. So we have that z squared plus r squared equals 4. And so you see that z will be root 4 minus r squared at the highest point. And so there, z starts at 0, but it doesn't go all the way up to the height 1. It gets intercepted by this sphere. And it works this out. So those are the two integrals that you have to do. And by the way, this is very similar to the situation over here. 4 minus x squared minus y squared is the same as 4 minus r squared, because x squared plus y squared equals r squared. All right, so they actually compute those integrals. It's not so hard, but there's two of them. Okay, so just to show you how it works, I'll just do them, because it's the first triple integral. This one, I noticed that, okay, the 1 is just 1. All three integrals can be split apart because there's no dependence here. None of these are all numbers. So you just have the dz part. So the first integral, you can just do 0 to 1 dz times from 0 to root 3 r dr and 0 to 2 pi d theta. And I'll come back to that. But for the second integral, nothing depends on theta, so I can pull out the theta. But the other part I have to do, I actually have to do. So I have an integral from root 3 to 2 of r d, well, first of all, of the z. So it's going to be the integral of 1 dz is z evaluated between 0 and root 4 minus r squared. And then I have r dr. So I pulled out the theta. Okay, so let's go back to this one. It's really simple. It's 1 times r squared over 2 between 0 and root 3 times 2 pi. As for this integral, it's 2 pi times the integral from root 3 to 2, and z, it's just r root 4 minus r squared dr. So I have to do a little bit of work. The first one, when I plug this in, turns out to just be 3 pi. Whereas the second one is 2 pi times the derivative of 4 minus r squared is 2r. So the change of variables will give me a half 4 minus r squared to the 3 halves. And then I better multiply by 2/3. So this is just one variable integration. I've done it a little bit quickly, but there it is. So you get 3 pi plus 2 pi over 3. And when you plug this in, this should be a minus actually as well. So when you plug this in, the 2 goes away and the 3 just becomes 1. It's 4 minus 3 as it turns out. So this all simplifies, if I'm not mistaken, to 3 2/3 pi, otherwise known as 11 pi over 3. I think that's right. All right, so that is the solution, assuming I got the last integration right, as presented in the solutions that you find online on the website. But I don't find it to be a very good solution, because I think it should have been done in the other order. Let's look at that, and then we'll do spherical coordinates. Then we'll look at another example, I dare say. I want to show you how this problem should have been done. Okay, look at this. Look at this picture again. Notice that when we picked our r theta, we had two different regimes of z. One when you're inside and you're hitting this top flat bit, and the other one when you're outside that annulus, or outside the middle circle. But what if instead you had done it in this order? So instead of this dz first, you did r dr dz d theta, and you still have a 1 because it's a volume. What if you did that? Well, now it's saying fix a theta and a z. So the angle doesn't really matter, but let's fix a height z. And ask yourself, where does the projectile come out? It doesn't matter what angle you're in, you fix a z. So there's my fixed z, and here's 0, and I'm interested in when does r leave? Well, hey, this is z, this is r, this is 2. You'll find that no matter which height you're at, r leaves at root 4 minus z squared. It doesn't matter which height you're at. R always goes from 0 to root 4 minus z squared. So that's all you need to do, root 4 minus z squared. And then the z goes from 0 to 1, and the theta goes from 0 to 2 pi. There's only one integral to do, and it makes a lot more sense. So if you do it, again, I'm going to pull out the d theta part. The r integral, look how much easier this is. The r integral is just r squared over 2 between 0 and root 4 minus z squared. So you get 2 pi times 1/2 from this, and it's just the integral from 0 to 1 of r squared dr. No, not r squared, 4 minus z squared, because you square root and you square. Much easier integral to do. So it's pi times 4z minus z cubed over 3 between 0 and 1. So you avoid the square root as well. You plug this in and you get 11 pi over 3. Okay, so I don't know why the solutions have that other method. It's setting a very bad example. When you have a cylindrical coordinates thing, you should try to make your life easier and find the direction of integration that's easiest. So I really think that it's very important that you understand, nevertheless, how to do it both ways, and why the thing splits up in one and not in the other, and indeed the mechanism. So before I move on, are there any other questions about that example? All right, well, I better do spherical and an example of that before moving on to line integrals so that I can get through the course by Thursday evening. All right. So spherical, it's similar to cylindrical, except that instead of having one angle, you have two. And then you have a radius, and that's it. So here goes. Let's look first at the geometry, and then the coordinates and the transformation, and then some examples. In fact, I want to do that same example, setting it up. Okay, so here goes. The geometry is this. X, Y, Z, X, Y, Z. Okay, you have some point in space. Now what you care about is rho, which is its genuine distance here. r is the distance to the z-axis. So this angle here down from the z-axis is phi. So let me write the rho over here just to not get it in the way. This angle is phi. Okay, so think of z as the North Pole, and wherever my point is that I'm trying to describe, I need to describe how far down to go. And so actually 0 is the North Pole, pi over 2 is the equator, no matter where you are, which way you're facing, pi over 2 is the equator, and pi is all the way at the South Pole. There's no need to go past pi, because instead of going like that all the way around, you might as well have turned around and just gone less far. So you only need phi to go to pi, not 2 pi. On the other hand, when you drop this down to the axis, you still have the good old theta from before. So theta is exactly what it was before. You project the point down and measure the distance to the x-axis. So in a sense, theta tells me, I kind of need to know theta first. So here I am at the North Pole, or at least pointing to the North Pole. I need to know where to turn. So I'm facing along the x-axis, and I turn an angle of theta. Then I go down an angle of phi, and then I go a distance of rho, and that gets me to where I want. So I've just been able to describe any point in space by starting at the center, the center of the Earth, if you like, or the central point, and telling you the two angles followed by the distance to go once you're pointing in the right direction. So it's very important to know that geometry, but it's also important to know what the formulas work out to be, which by relatively simple trigonometry, you need to know that x is rho, and then you'll have a cosine phi, and then a sine, rho cosine theta. Actually, it's better to do it as sine phi, cosine theta. There we go. Then y is both sines, and z is rho cosine theta. So the reason I write it like this is sort of x is r cosine theta, y is r sine theta, and z is now something else altogether. So I don't know how to help you memorize that, but that's you've got to know that. So this is critical. And then once you have this, obviously the most useful thing to know about this is that x squared plus y squared plus z squared is rho squared. But you need to know the Jacobian dx, dy, dz. Do not forget to replace this by, you need a rho squared and a sine phi to make this work. D rho, d phi, d theta. That's the Jacobian of this transformation. Okay, so everything else is just examples. But in order to set it up, we kind of have to know what we're doing. The order is d rho, d phi, d theta, and that's very much the most used, the usual, or the most used order. So let's see how it works. What we're going to do is we're going to take the same damn shape, the spherical cap, and we're going to do it in spherical coordinates, because actually that's what the last part of the problem demands. Again, that's a problem from a final. So here goes. We're going to pick a point. So in order to pick a point, we've got to fix the phi and the theta. So we're dealing with some ray. So we have to start with a ray and see where we go out. Let's take that ray here. Where's rho? 0. Where does it come out? This distance. So we need rho out. Rho in is nothing. If this is the ray, rho out is equal to 2. So for some of the rays, rho out will be 2. But unfortunately, some of them are more complicated. This is different. So we'll come back to that. Okay, so my question is, which rays? So you've got to look at this in terms of two angles. One is this angle here, which is phi, and the other is the theta angle. Now, how much does the theta angle matter to whether you're going out of the curved section or out of the flat section or not out at all? How much does the theta matter? And the answer is it doesn't matter. The problem is completely symmetric about the z-axis, which is why the cylindrical coordinates work so well. So theta doesn't matter. The only thing that matters is phi, and this is extremely common. Most of the problems I have to tell you, the theta doesn't matter. It almost always goes from 0 to 2 pi. When I say most of the problems, I mean in previous Math 201, not necessarily in real life, in Math 201 finals. So what I advise is that you always draw these things to be essentially in the YZ plane, so it's flat. And now I ask you this. In the YZ plane, the thing looks like this. Here's the situation. It's just a semicircle, 2, but the height 1. We've chopped it off. It's not very good drawing. And here's the phi. And I want to know, for what values of phi do you hit this curved surface here? That's the question. You need to use some geometry probably to do that. Here's 1. For what values of phi do you hit the thing? Well, the radius is 2. And the height is 1. So we have cosine of phi is 1/2. In other words, phi is pi over 3. You need to know your trig. Okay, so the situation is this. If phi is between pi over 3 and this, well, what is this? 0, pi over 3, pi over 2, and so on, down to pi. But if phi is between pi over 3 and pi over 2, you will go out at 2. You start at 0 and you get out at 2. So one piece goes like this. The curved bit, you have this integral. Theta goes from 0 to 2 pi. Big D goes from pi over 3 to pi over 2. And rho goes from 0 to 2. And then you've got 1, and then you have that volume element, always rho squared sine phi d rho d phi d theta. Unfortunately, that is only one piece. Now, can anyone describe to me what geometrical object, by the way, this integral gives you the volume of? How would you describe it? I'll ask a question to the field. Sorry? It's not the cone. It's not a cylinder. It's this with the cone chopped out. It's a volcano. That's what that's the technical geometrical term. No, it sort of, yeah, I mean, I guess it sort of is. You don't get the cone. You get this figure revolved around the z-axis. That's what you get, because the theta being 0 to 2 pi gives you the revolution. Phi going only from pi over 3 to pi over 2, given that phi equals 0 is up here, gives you this. And rho going from 0 to 2 gives you that. But what is the other piece? Well, in order to do the other piece, I have to work over here. And then the final answer is going to be the sum of those two, and much nastier to work out. And the exam question did not require you to work it out. It just said use one of the ways. Okay, please. Let's do the other one. First a question.
If it just asks you to find volume, could you do it as a double integral and then a surface of rotation?
Yeah, I guess if you just had to find the volume. So the question is, if you just had to find the volume, could you use just your regular... You could even do it as a single integral using cylindrical shells or something like that, right? Or the disk method. But the question said, set it up using cylindrical. It did not say rectangular. The question was, do it in cylindrical and do it in spherical and use one of them to compute the volume. That was the actual question, as you'll see if you look it up online on one of the previous papers. It's one of the recent ones. Okay, but I want to do one of the... So I want to do the interior of the cone. That's what we're left with. So what I'm trying to say is that if rho happened to be instead, if rho happens to be between 0 and pi over 3, that's a bad picture. I can salvage it without redrawing the circle. There we go. That's a bit better. Then the question is, so here is my I said rho, I meant if phi. If phi happens to be between 0 and pi over 3, we need to know where is the rho out. And it will occur when you hit the top of this cone. So that's all we're left with. We've done the other bit. It's ghosted out now. This is the last little bit. So watch this. Again, the whole thing is symmetric in theta. So here's my picture. The cone becomes a triangle of height 1. The radius becomes this side of the thing, 2. And then the question is, here is an angle phi. Right, there's my phi. And I need to know what is the r out, which is this length here, rho. Okay, in other words, well, that's too small. I got to redraw it. 1, 2, angle phi, and I need this distance here, because the rho in is 0, and the rho out is at the top of the cone. So how do you work that out? Well, you need to use a little bit of trig once again. So this height is 1. This is phi. The 2 isn't particularly relevant, as it turns out. You just do this. You do cosine phi is 1 over rho. So rho is secant phi. You take reciprocals of both sides. So that's the rho out, if you like. Rho in is 0. So the other piece goes like this. Triple integral. Theta is going from 0 to 2 pi. I might as well write this out first. It's rho squared sine phi, as always, d rho, d phi, d theta. So theta goes from 0 to 2 pi. We decided that phi is going from 0 up to pi over 3 before it starts encountering the curved bit. But rho goes from 0 to secant phi. And if you were to work out that integral, it would not break up. The theta bit can come out of it, but you cannot split off the phi bit because of this. The secant phi is screwing it up, whereas you could in the other piece. So the other piece is over here, and nothing depends on anything. You could break them up into 3 integrals. Okay? Now, just stare at the 2 pieces. They're sort of separate boards, but see here rho goes all the way from 0 to 2, but phi is between pi over 3 and pi over 2. The other piece has phi going between 0 and pi over 3, but now the rho depends on phi. So it's a little bit different. So you have to be able to deal with both pieces and understand this. All right, I'm not going to spend any more time on examples on triple integrals because I suspect we'll be spending plenty of time on Thursday doing that. So what I'd like to do in the last 20 or so minutes is move on to line integrals so that we can set up tomorrow and get through everything that we need for the rest of the course. But I could take one quick question about triple integrals or something like that, if there was one. Well, if you do have one, then you could call it out in the next 5 seconds. No? Okay. Line integrals. So the deal with the line integral, as I said, is that you have an integral like this, where C is some curve. So it's a little bit of a different thing. We're adding up the values of f along a curve. And the curve could be in a plane or it could be in space. I'm going to deal with space, I guess, more than a plane, because if you can do it in a plane, you can do it in space. Oh, by the way, I sort of skipped Jacobians in 3 dimensions. Technically, it's in the syllabus, but I've never seen an exam question on it. So I prefer to be practical and just say, well, look, it's the same thing except in 3 dimensions. And show me an example and I'll do it on Thursday. All right, so let's go with something that is almost sure to come up, namely some sort of line integral will probably come up. Now, if you have a simple situation like this, you cannot just compute it like you would a regular one-dimensional integral. You have to convert it, or I said in my picture right at the beginning of the session, reduces to. you have to reduce this to a regular integral. And the way you do it is by parameterizing c. So to do this, you have to convert it by parameterize c as this. It has to be r of t equals x of t, y of t, and if there are 3 dimensions, it'll be z of t. If it's only 2 dimensions, then you sort of ignore that. Ignore in 2 dimensions. Okay, so you have to be versatile about that. I'll do a 2-dimensional example soon. So, okay, you find this r, and so there's a velocity vector v. V of t, as we saw before the midterm, is the same thing as the derivative. So you just differentiate all of these. Just differentiate. Well, that's nice. Then you need to know the formula. World, you can replace ds by the absolute value of v of t, the velocity vector dt. That's sort of the canonical thing. So if your parameter is t, the way to convert it is to a proper sort of regular old integral. The ds you cannot just replace by dt, you need to replace it by the velocity. So that's sort of the length of the bit of the curve, actually, as it turns out. The speed vector gives you the length. So you take the absolute value of this, and that's how you work this out. So look, here's a question that just does nothing other than what I just told you. And I found this in one of the older finals. And the length of v, yeah, that's the length of the vector. That's the speed. V is the velocity, and the length of it is the speed. Okay? So, here's the question. There is a spiral. C is the curve. R equals b e to the theta in polar coordinates. So this is a spiral in the xy plane. And here, b is a constant. B is a given constant. And theta goes from 0 to 2 pi. Okay, so the question is, compute the integral of root x squared plus y squared ds. So you don't need any fancy stuff. It's not a vector field or anything. It's just an application of what I just told you. So you somehow need to parameterize the thing, but there's also a little polar coordinate complication. But never mind. Let's just do as we do. The parameterization that you should use is this. X is r cosine theta, and y is r sine theta. However, that's just general polar coordinates. We need one parameter. So we need to get rid of either r or theta. But it's clearly easier to get rid of r because you're given that r equals b e to the theta. So actually x is b e to the theta cosine theta, and y is b e to the theta sine theta. All right, so what does this give us? In my previous notation, the vector r, which is not to be confused with the little r, the vector r, this is an r, of theta is equal to the x comma the y. Okay, the only difference between this and the prototype is that I am using theta instead of t. And theta goes from 0 to 2 pi. Okay, so the velocity is just the derivative. So I have to just differentiate this. And it's a bit of a mess, just a product rule though. You get v du dx, so it's b e to the theta cosine theta. Unfortunately, then you have to add on u dv dx. Remember, b is a constant, so I'm not going to do anything. The derivative of cosine is minus sine, so you're going to get b e to the theta sine theta. Comma, now do the product rule on this. You get b e to the theta cosine theta plus b e to the theta sine theta, because the derivative of e to the theta is 1. So that's the product rule on both terms individually. And we can tidy this up by pulling out the b e to the theta, actually. That's kind of classy. It's a scalar that is in front of everything. So the x-coordinate is cosine theta minus sine theta, and the other one is cosine theta plus sine theta. So that is the velocity vector. The length of the velocity vector, which we're going to need, is the absolute value of b e to the theta. I should have said b is constant. Let's say it's greater than 0, whatever. Actually, you know what? It didn't say it was greater than 0. It just said b is a constant. Yes? Sorry?
Why is it a spiral?
Why is it a spiral? It's a logarithmic spiral. It doesn't matter. I mean, you have to draw it and you'll see. It looks like this. When theta is 0, it's just b. And then as theta increases, the r gets bigger. So by the time theta's gotten up to 2 pi, it's gotten all the way up to e to the, b e to the 2 pi. It's called a logarithmic, actually it's not a logarithmic spiral, it's a regular old spiral.
So that's like e to the x?
No, because it's in polar coordinates. Anyway, I'm not going to, it's nice to know what these things look like, but it's actually not necessarily this particular problem. We just need the square root of this mess. Cosine theta minus sine theta all squared plus cosine theta plus sine theta all squared. And notice that I just took the absolute value of b e to the theta. It's kind of a nice little trick there. I mean, it wouldn't be a crime to leave it in every term here, but it'll just pop out of the square root as an absolute value anyway. So we went this out. E to the theta is positive, but I don't know about b, so I can just write this as absolute value of b times e to the theta. As for this stuff in this square root here, I have cosine squared plus sine squared plus cosine squared plus sine squared, so there's 2 of them. And then if you work it out, you'll get minus 2 cosine theta sine theta and plus 2 cosine theta sine theta. So actually, it's just root 2 b e to the theta. Beautiful. So we can now finally come over here and say that the integral we're looking for, root x squared plus y squared ds, is equal to, in the parameterization, x was equal to b e to the theta cosine theta. So this is, I'm not going to have enough room. B squared, well, let's just write it as b e to the theta cosine theta all squared plus b e to the theta sine theta all squared. Of course, you could just recognize that's just r and replace it by b e to the theta anyway. But ds is equal to this junk. ds is v of theta d theta. So it's this junk, root 2, absolute value of b, e to the theta, d theta. So you absolutely have to have this in. And theta was said to go from 0 to 2 pi in the question. So I'm going to fill that in. And I have converted my rather nice looking but completely impenetrable line integral into a regular old one-dimensional integral, which can be simplified considerably. I'm going to pull out the root 2b like this. Root 2 absolute value of b. And then I have this is just the cosine squared plus sine squared. So you have the absolute value of b e to the theta once again. You have another e to the theta d theta. And I'm being sort of anal about the absolute values. I mean, if b was positive, everything would just pop out. But as it happens, I have e to the theta is positive, always. And I have 2 lots of absolute value of b, which is just b squared. So it's root 2 b squared, integral from 0 to 2 pi of e to the theta, which is e to the 2 theta. And if you work this out, you should get root 2 over 2, because of the division there, b squared, and it will come out to be e to the 4 pi minus 1 as a factor. Don't forget that e to the 0 is 1, and cannot just omit that term. Okay, so that's sort of a basic computation, but a bit of a messy one of a line integral. Now, I don't have too much else to say about line integrals. And next time I'm going to start with conservative vector fields and finish off the course. So it's pretty much halfway through. It's more or less what I said I was going to get through today. Look, a different form of line integral is like this. Okay, come on, 5 minutes, you can do it. Suppose that you have, instead of this type of problem, you have a vector field f. So that's already a vector itself, dot dr. I'll just do this in 2 dimensions for the moment to make it simple. So this is what I call the work integral, or a flow, or a circulation integral. The way you do this is the same, but it's even simpler. You don't even have to compute an absolute value. What you do is, again, you parameterize this thing like this. R of t is equal to x of t, y of t, say. So dr is exactly what you did previously. Differentiate exactly as you did. You don't need vectors here, sorry. But now you have a dt. And then f, on the other hand, f is equal to some vector, m comma n. I don't know, these are functions of x and y. Stuff in x and y, which you can convert into m of t. I'll call it m twiddle, and n twiddle of t. This is what you get by plugging in x and y as functions of t. So you plug in the parameters. Well, once you've done that, you just convert this. Well, I mean, you'll have some stuff in x and y here. So this could be x plus y, this could be x minus y squared. And you know x and y in terms of t. And then you just plug it in and you get f in terms of t. So you have dr is some function of t as a vector, f is some function, and then you just take a dot product. And if you do, it basically looks like an m dx plus an n dy, which is the other form of the thing, as a differential form. But this makes a lot of sense when you actually compute the thing. So let's just sort of finish off today with one computation which I'm just going to make up. It's not, I don't have a specific example at this point, although they will come up as we do examples of the main theorem. So in our last 2 minutes, here's just an example. Suppose that f is the field x plus y, comma, I don't know, what do I want to do? Cosine, no, I'll just do x squared, what the hell. Okay, I hope this works out. And I want to find the integral, so C is the circle. X squared plus y squared equals 1. And the question is to find, as it happens, it's once around counterclockwise. It happens to be a closed circle, closed curve. So find f dot dr. No, it doesn't have to be closed. The other example wasn't closed. It was a spiral. It doesn't have to be closed here. If you call it circulation, it has to be closed. If you call it flow, it doesn't. In Green's theorem, it has to be closed. But we're not doing Green's theorem yet. All right. So here's how I approach this, whether or not I finish the integral. I'm going to use theta again because it's a circle. So I'm going to let x be cosine theta and y be sine theta. And why do I do this? Why not r? Because it's the circle x squared plus y squared equals 1. So I have, in other words, r of theta is just cosine theta, sine theta. So dr, I don't even need of theta anymore, dr is equal to minus sine theta, comma, cosine theta. So that takes care of the r. Now the f in x and y terms is x plus y, comma, x squared. but I need to convert this into theta terms. So this is going to be equal to x is cosine theta, y is sine theta, so it's cosine theta plus sine theta, comma, cosine squared theta. All right, so f dot dr, well, I can even do this integral. This integral now is the integral of this quantity, cosine theta plus sine theta, comma, cosine theta. That vector is f, cosine squared, thank you, dot dr, which is minus sine theta, comma, cosine theta, d theta. So I left out actually over here a d theta. I'm sorry, if you're going to write dr, you need a d theta. Over there I wrote the velocity vector, but I didn't have a d anything, I just wrote v. Here I'm going to have to do dr d theta. And theta goes from 0 to 2 pi. So when you take the dot product, it's just this times this plus this times this. And if I'm not mistaken, it works out to be this integral. Cosine theta times minus sine theta minus sine theta times sine theta plus cosine, so that's this term times these two, plus this term times this term. Now, it may well be. I mean, you could definitely do that integral. That's a substitution, that's a half-angle formula, and that's a trig thing. Now, I don't propose to do it because it turned out to be a little bit messy, but there's a regular one-dimensional integral that you could do this. You could do this as use Math 104 techniques. Okay, so there's nothing to be scared of about the f dot dr. In fact, it's even easier because you don't have to take square roots and deal with this sort of business here. All right, so that's the basics of line integrals. Next time we'll look at this conservative vector field stuff, surface integrals, and all those three theorems. That's the entire thing. Thanks.